morning. It is Wednesday, April 29th. I'm happy to see you. I'm sorry it's a little bit shaded out here on my patio, but it's just so nice that I didn't want to miss an opportunity to be out here, even though I'm sort of in a little bit of a shadow. One of the things that I want to start with is, so when we're talking today, we're going to talk about how energy is transferred when work is done. And for today, I really want you to think about that concept. So when we're doing work, we are transferring energy. So here's a concept that I want you to think about. This is actually your discussion question for the day. And so you will be able to think about this as we're talking. And I want to go over the vocabulary words, first of all, that you need to be aware of when we're in this part. Potential energy, kinetic energy, mechanical energy, and then we want to talk about the conservation of energy. So this is what I want you to think about. Listen to this scenario. A school carnival sometimes includes a dunk tank. The goal is to hit a target with a ball and causing a person sitting over a tank of water to drop into the water. You do work on the ball as you throw it with your arm. If your aim is good, the ball does work on the target by striking the target. How do you transfer your energy to the ball? So that is our discussion question today. So work transfers energy. When you change the position and speed of the ball in the carnival game, you're transferring energy to the ball. Energy is the ability of a person or an object to do work or to cause work to be done or to cause change. When you do work on an object, some of the energy is transferred to the object. You can think of work as the transfer of energy. In fact, both work and energy are measured in the same unit, which is joules. So that is the thing to think about in terms of the carnival unit. So the other thing that happens is that work changes potential and kinetic energy. When you throw a ball, you're transferring energy to it and it moves. By doing work on the ball, you give it kinetic energy, which is the energy of motion. Any moving object has some kinetic energy. The faster an object moves, the more energy that it has. So the more energy had to be there for it to go faster. When you lift a ball from the ground, you give the ball a different type of energy. It's called potential energy. Potential energy is stored energy, or the energy an object has due to its position or its shape. So the potential energy that you've given it is the potential to drop. So you've lifted it up, so it's sitting up. So if you let go of it, it is going to drop. And so when you're holding it aloft, it is potential energy that you have. The other thing is we're going to talk about how we calculate gravitational potential energy, because remember, potential energy has a couple of forms. The one we give the ball when we lift it up is potential gravitational energy. So the formula for that is gravitational potential energy equals mass times gravitational acceleration times height. So we've got three variables there. So GPE, which is gravitational potential energy, is equal to mass times gravity or gravitational acceleration times height. And I will give you a sample problem to work as part of your work today. And that'll be a gravitational potential energy practice math problem, so math connection. So, and then here's another example I think that you should think about, and that is jumping on a trampoline. When you're jumping on a trampoline, when you're up in the air, you're suspended for that fraction of a second, you have potential energy based on your position. When you're going down, you have potential energy is turned into kinetic energy, and you have velocity when you go down, so you're going to go faster. And then the trampoline, once you land on the trampoline and it pulls down, we've got that elasticity there, and it pulls down. At that time, you've once again created potential energy because you're holding down the potential energy that you created is that pull down, that stretch, and it's going to fling you upward. So while you're down there for that fraction of a second, you are you have potential energy again. All right. So those are things to think about. The other math formula, and remember today I told you guys I would attach a formula sheet for you, so I'll do that at some point today. So calculating kinetic energy, the formula is kinetic energy equals mass times velocity squared divided by 2. Another way you can look at that is kinetic energy is 1/2 of mass times velocity squared. I'll put both of those there. You're also going to have a sample problem to work using that kinetic energy formula. So the other thing we want to talk about is how we calculate mechanical energy. And remember, we talked a little bit yesterday in our office hours call, and I also mentioned in the video on Monday that we're going to be talking about the different types of energy that we had discussed briefly at the beginning of last week. So today we're talking about mechanical energy. And mechanical energy is the energy possessed by an object due to its motion or position. In other words, it is the object's combined potential and kinetic energy. So once you calculate an object's kinetic and potential energy, you can add the two values together to find the object's mechanical energy. So the way we calculate mechanical energy is potential energy plus kinetic energy. So ME equals PE plus KE. So again, those formulas are going to be available for you in a sheet. And one of the things, again, to look at is mechanical energy is related to kinetic and potential energy because we calculate it by combining those two things. All right, so the other thing that we have to go over today is the law of the conservation of energy. And remember, we've had conservation of momentum, we've had conservation of everything, and that is because like conservation of matter, energy is neither created nor destroyed. It just changes shape, changes position, changes form, just like matter does. So total amount of energy is constant. You know that energy is transferred when work has been done. So once you throw that ball at the dunk tank, the ball has moved. So energy has been expended and work has been done. So no matter how energy is transferred or transformed, all of the energy is still present somewhere in one form or other. This is known as the law of the conservation of energy. As long as you account for all of the different forms of energy involved in any process, you will find that the total amount of energy never changes. That is the definition of the law of the conservation of energy. So we also look at conserving mechanical energy. So if you have an inline skater, you know how they can go up the side of those ramps, and some of them are really very good, and they can flip up and they can balance on a hand, and then they come back down. As they roll down the ramp, the amount of kinetic and potential energy will change depending upon their position, and we talked about this last week. If you are have a pendulum, if that ball is pulled all the way to the side, it has 100% potential energy. Once you let it go and it starts moving, the amount of kinetic energy will increase and the amount of potential energy is going to decrease. So that's constantly in motion. But that is also because it's conserved. So you can only ever have 100% potential energy, and you can only ever expend 100% of your kinetic energy. So the total mechanical energy, therefore, is going to stay the same. You can't get 120% of something. You can lose mechanical energy. So if you think about, again, that pendulum is a fixed object on us that's suspended from a fixed support. So it can swing freely back and forth, free from the force from the influence of gravity. So it's going to go back and forth, back and forth. As the pendulum swings, that potential energy is converted to kinetic energy. And then as it goes to the top of one side, we've increased our potential energy again and decreased kinetic. And it's going to go back and forth. However, you also have friction. So air, any object is going to slow. And we have to remember that air is matter. So as an object is moving back and forth, you might think, well, okay, well, depending upon Newton's law, first law, the law of inertia, if something, it's only if something interacts with that object, it should just keep going, right? Back and forth forever. But we do have something interfering with it, and that something is air. And air can cause friction as that object moves back and forth. That is how the pendulum slows, and that is how we lose that mechanical energy. So it's being transferred out somewhere. Well, think about this. If something moves through the air, what's it doing? It's moving the matter of the air. It's pushing particles. It's moving them around. So that too is transferring energy. It's transferring energy to the air particles. But the air particles, as they come into contact with that pendulum, are going to slow that pendulum because it creates friction, and friction is force. So you see it slow because there is something interacting with it. There is something acting upon that object. So that's, in a way, how we're losing that mechanical energy. Okay, but again, we're not losing it. We're losing the mechanical energy because work is being done and there is something interfering with that pendulum, but the energy is just being transferred elsewhere. If we could pull it all back, it would still equal the same amount of potential and kinetic energy combined. All right, but remember that it's being dispersed out, it's being moved. All right, so the last thing we're going to go over today, and I'm going to give you the definitions, and I will read these in terms of the forms of energy. And we've already talked about mechanical energy, so we're going to talk about thermal, chemical, nuclear, and electromagnetic. So thermal energy, so first of all, I'm going to remind you, mechanical energy is a combination of potential and kinetic energy combined. Thermal energy is the energy an object has due to the motion of its molecules. All right, so the faster the molecules in an object move, the more thermal energy that object has. And for this, think about putting a pan of water on a stove, turning on the heat, and waiting, and what starts happening. As that heat energy is applied to the pan, that heat is then transferred to the water molecules, and as they heat up, they begin moving, right? So you start getting little tiny bubbles on the bottom of the pan, and eventually you've got rolling bubbles as that water is boiling, okay? So the faster it moves, the more thermal energy is actually being produced. We have chemical energy. Chemical energy is the energy stored in chemical bonds that hold chemical compounds together. If a molecule's bonds are broken or rearranged, energy is released or absorbed. When Oppenheimer created the atomic bomb, he split a hydrogen atom, something that had never been done before. And it completely shocked everybody when they first started doing these experiments that a hydrogen atom could create so much force. But what they've done is basically broken one of the laws of nature, because you don't normally split an atom. So that caused a tremendous force and explosion. Energy can be absorbed. I want you to think of your skin. You're absorbing energy from radiation. Chemical energy is used to light up fireworks displayed. It's also stored in food and in matches. Nuclear energy is the potential energy stored in the nucleus of an atom. In a nuclear reaction, a tiny portion of an atom's mass is turned into energy. The source of the sun's energy is nuclear energy. Nuclear energy can be used to run power plants that provide electricity. We then have electromagnetic energy. This is the energy associated with electrical and magnetic interactions. Energy that is transferred by electrical charges or current is often called electrical energy. Another type of electromagnetic energy is radiant energy, the energy carried by light, infrared waves, and X-rays. Remember, it is possible to transfer or convert one form of energy into one or more other forms of energy. So that is a key thing. And remember, we also have conservation of that energy. Okay. I want you to think about this one last example. You rub your hands together on a cold day. What you're doing is converting mechanical energy stored in the mechanical energy of rubbing your hands together to thermal energy. You're using that friction. That friction is causing molecules to move, and that is creating thermal energy, which is heat, which is going to warm up your hands. All right. So remember that we can convert from one to another. All right, that's all I have today. Remember, we've got our one-on-ones today for oral presentations from 1 to 2 o'clock. I've also scheduled a couple of individual ones. I think I have one at 12:15 as well. I'm happy to do additional ones between 12:15 and 1. That's extra time available. I will put that in your classroom stream as well, so if you want to do that, you can. But between 12:15 and 1, you might just have to sit in the waiting room for a little bit. Okay? Have a great day. It's going to be hot today, but get a moment to step out into the sunshine. Later today, I'm going to do a little bit of gardening just to kind of clean up a little bit. And I'm looking forward to that after grading all your work. All right. Have a great day, guys. I miss you. Bye.